In this activity, your goal is to derive the differential equation models of the circuit using Kirchhoff's current and voltage laws. So go ahead and press pause and work through this activity, discuss with your friends, and then take a look at my solution. So there are many ways to approach a problem like this, but I'll show you one of my preferred approaches. So one of the important things when you're looking at these Kirchhoff and voltage and current laws, especially the current law, is that there are equitable ways of drawing the circuit diagram. So in this case, we have this source, and then we have this branch that extends into all of these. And one of the things to keep in mind is that these wires effectively, they're all connected, and so they all have this same amount of current and voltage going through them. So really the idea is that this is connected, and at some point in time this branches into the inductor, into the capacitor, and into a resistor. And then these all connect. Let's see, so these two connect and go back to the source. This one actually goes forward and then splits into the second capacitor and the second resistor. And then these come back together and come back. And so this is another way of viewing this, and this kind of helps identify the fact that this first current separates out into IL, I1, and I3. And that's maybe a little bit easier to see in this version of the diagram than the original one. Similarly, this means that IL enters this junction and separates out into I2 and I4. And so looking at it this way kind of helps us identify some of these Kirchhoff current laws a little bit easier. So like we were just mentioning, we can identify those circuit laws, namely the current laws, pretty easily. And that is these two expressions that we used before. And again, that's really just looking at the current splitting into other currents. Now, one thing to kind of keep in mind before we use our next Kirchhoff law is simply just to understand what we expect in terms of differential equations here. In this case, we have two resistors, two capacitors, and one inductor. The resistors are essentially, because their circuit law is just V equals IR, this is a static relationship that does not have a differential equation as part of it, whereas the capacitor and the inductor have derivatives involved. And so each of the resistors will not contribute a differential equation, but you can kind of think about each of the capacitors and the inductor as being a dynamical element, which is essentially introducing a derivative or a required derivative in order to model what's going on. And so for that reason, we expect to have three differential equations that come out that describe this circuit. So we can kind of have that in the back of our minds as we go through this, knowing that that's where we're moving. And so this comes out after we do some of the substitutions in this case. So for example, these two first equations don't have any derivatives in them yet, and that's because we haven't substituted in any of the remaining circuit identities. So our last observation, which allows us to essentially write down some equations, comes from Kirchhoff's voltage law. And one of the reasons that you can see that this is interesting is the fact that effectively this inductor splits the circuit into this part over here and this part over here. And those are in parallel with each other. So you can imagine these guys are in parallel with these guys, but there is this inductor in series in between. And so one of the ways to find this expression is simply just to, for example, take this particular loop. So you could take a number of different loops. You could take this loop instead if you wanted to, but this one's the easiest. This one that's in the middle here, this one's the easiest and allows us to write essentially V1. So we can go against the current and get V1, and then we can go with it to get across L, the inductor, and then across the capacitor. So that means essentially that the signs will be different between V1 and VL and V2. And so notice it doesn't matter if you have minus V1 plus VL plus V2. So the important thing is the difference in sign there. So now that we have these Kirkhof relationships written down, now the problem reduces to plugging in identities that we know. And so, for example, we know the current across the resistor. We can substitute the V equals IR to get this expression. We know the current, how to express the current here in across this first capacitor by using the capacitance times the derivative of the voltage across that. And then in this case, IL, so IL is something that we could substitute for, but because the expression for the inductor looks like VL is equal to LIL dot, so the derivative of IL, it's more difficult to use this as a state, use IL as a state. So instead we want to we're interested in keeping it as a derivative and then thinking about that element that has the derivative on it as the state. So in this case, we're going to keep IL there. So in the second equation, we can also keep IL around and then substitute in for I2 for the capacitor. Again, we get that form, and then the resistor here. So by the same logic as what we just talked about with IL, we can look here and notice that V1 appears with a derivative. And that also implies that V1 should be one of the states, because now we're going to take a derivative of it. So we won't substitute in for V1. And then the same thing happens here, and this says that V2 has a derivative on it, and so that should also be one of the states of our system, and so we're not going to try to substitute in for that if that appears in an equation. And so that's what happens down here at this last equation. We have VL, for which we have this expression and can substitute in LIL dot. And the reason why we're motivated to do that is because VL is not one of our states. We've chosen this IL as one of our states because it's what we've taken a derivative of in the inductor relationship. So in this case, this is VL, and then we've already decided that V1 and V2 are our states, and so now we can just write V1 and V2 and keep them there because those are our states. So again, our dynamical elements for this circuit are the two capacitors and one inductor, and so for that reason it makes sense that the voltages across those capacitors are our states because those are what we're going to have derivatives on. We're also going to have a derivative of the current across the inductor, and so that's going to be another one of our states of our system. And so then what is it that's driving this circuit? What's driving this circuit is the current that's being applied. And so if that current were to change, then that means that the dynamical elements of these capacitors and inductors would then alter due to that. So these are the system of differential equations that describe this circuit being driven by the current I, which is located right here. Eventually, in a subsequent class, we'll rearrange these into a kind of more usable framework or format, but for now, this is a perfectly fine way to leave this, this set of differential equations. And again, it's important to note that they're coupled in the sense that the derivative here is on V1, the derivative here is on V2, the derivative here is on IL, but all of these terms are in all of these equations, which is what makes them coupled.